Hello community! Today we build a company-specific transformer architecture on company data. So what we're gonna do? We're gonna pre-train a transformer from scratch. We're gonna fine-tune this transformer, and finally I show you how to run inference. So finally we can start coding. We are here in a Jupyter Colab notebook, and as you can see, we will pre-train a transformer from scratch. We will fine-tune it, and I'll show you how to do the inference. So first step, we will set up, then we will pre-train our transformer with the mask language model mask generator. Then we're going to fine-tune the model on a downstream task. We will use a classification task for our pre-trained BERT model. And when we have a fine-tuned BERT model, we will do some model inference. So great. I would say let's just jump right into it. Runtime, we need a GPU, yes. And here we go. At first, of course, we need KERAS and we need TensorFlow. And what I show you here with KERAS NLP, you know that KERAS in itself is a high-level API for TensorFlow 2. And they have a toolbox. And this KERAS NLP is a toolbox for modular building blocks. And you have pre-trained state-of-the-art models. And you can even go down to transformer encoder layers. And we will build our BERT model, our encoder stack with those layers from KERAS NLP. And it's so fast and it is so beautiful. And I have to show you this. So we install TensorFlow, we install KERAS NLP, it's running. Yes, beautiful. And of course, we need datasets. We need two datasets. At first, we have SST2 and then we have Wikipedia. Now, either you download it if you have it somewhere on an S3, or best thing, you go to Hugging Face, you go to datasets, you put in SST2, and you see you have a sentence and a label. 0 means it's a negative connotation, 1 a positive. And here you have everything. The Stanford sentiment tree bank is a corpus with fully labeled yes, yes, yes. And the other one, well, Wikipedia, you know Wikipedia, but this one is a version. Wikipedia 103 is 110 times larger than the other Wikipedia. You can have 100 million tokens. Yes, yes, yes. Beautiful. So on Hugging Face, you have within the dataset, you find every dataset that we need. So beautiful, we downloaded it and now we have it. Now I told you that we are operating here in TensorFlow. So we use here a beautiful command, tensorflow.data, that optimizes between our CPU and GPU or TPU processing. At first we have to have the pre-processing parameters. We have an input sequence length of 128 tokens. We have a masking rate of 25%. You can put it to 18%. You can put it to 21%, whatever you prefer. Let's make it a little bit more complicated. Let's mask 25%. And then, of course, you load your data with a beautiful TensorFlow data pipeline. Then we load our CSV files. Great. Batch size is not defined. Yes, of course, because I did not execute this cell. I am talking too much. Beautiful. So this is done. This is done. And if you want to have a peek, so get single element, show me. Here you have your sentences. Beautiful. Now we do not need a baseline. And here we go. Now we have now to pre-train a naked transformer. There's nothing, there are no weights we can have from download, from pre-train. No, we pre-train our own transformer. So what we need an additional layer, of course, and we have here the mask language modeling objective that we train it on, and we will not train it on the NSP, on the next sentence prediction. So great. Now you have to know that in this toolbox of KERAS NLP, there is a beautiful tokenizer. This is our word piece tokenizer that we need for the BERT model. Have a look at this. And we need something that is called a mask language model mask generator. I showed you in my last video when we did all of this in PyTorch that we had also a specific function to generate here the masking of our sentence token for us. Now here we have the command KerasNLP layers.mask language masks language model mask generator. Beautiful. And then, as I told you, we will use here TensorFlow data that we have here a pre-compute of each batch on a CPU, and the GPU or our TPU will do the heavy lifting, the training of the batch that came before. So we have an optimal resource optimization of CPU and GPU with our TensorFlow.data command. I have a specific video for you just on this command. And here we go. Now, for the tokenizer, you have a BERT tokenizer, or we go with the word piece tokenizer. This is the class command. I just want to show you that you see here all the parameters you can choose. Strip the French accent, yes, no, split it, yes. Split here on Japanese, Chinese, or Korean letters, yes. So beautiful, whatever you can do. Yes, I don't have to show you the example because this is clear. Or if you want to have a D-type string, you can have this. Beautiful. So now for the mask generator, this is the class. Those are the parameters. We're going to use the vocabulary size, the selection rate, the mask token ID. But let's have a look at this when we really do the computing. And yeah, I got a question about rect tensor. What is it? Just think about it as a variable length list. So a list with variable elements that have variable length. Think about this. Variable length features are the set of actors in a movie, or think about sentences that have a different length, different number of words in the sentences. Those are batches of variable length SQL inputs. So this is a rect tensor. So here we go. Of course, we need a lot of pre-definition. Pre-processing parameters. For the batch size of the pre-training, we go with 128. The fine-tuning, depending on your GPU, maybe increase it. 32 works fine for me on a free Colab notebook. The sequence length here is rather short. So I checked, we have just some short sentences in our data set, but please increase this to 256 or 512 or 1024. This is depending on your data set, the length of the tokens in a sentence that you have. Now, for the BERT model, for our encoder stack, the number of layers, or the transformer blocks, as it is called if you think about the original transformer architecture, normally you would go with 12 or with 24 or even higher. For demonstration purposes here, I just put it to 3. I also reduced the dimensionality to 256, and the number of heads is here with 4. For an operational example, you have to increase those numbers significantly. So number of layers, I would go with 24 or higher. Dimension 512 minimum. Dropout rate you can define. Beautiful. And then you have the learning rate for the pre-training and for the fine-tuning. The epoch we spend on pre-training, and the fine-tuning epoch. We will have to fine-tune our pre-trained system. Beautiful. We defined all of this. And here we go. As I told you at first, like in my video I showed you here on the PyTorch system, we need at first a tokenizer. And we have here from our KerasNLP toolbox the word piece tokenizer. These are our parameter. Then we need the mask language model mask generator as a layer. Those are the parameters, and then we are already done. We define now a function called preprocess, where as an input we have our tokenizer and then our masker that is applied to our inputs, and the masker is very simple. Our mask generator that does the masking of the tokens in our sentences. So what we get out of this is a feature where we have the token IDs and the mask position. Plus we get the labels and the weights. So what we have to return from this function is features, labels, weights. And then we do here with prefetch and the TF data auto-tune, we say, hey, system, auto-tune yourself, become the best possible configuration. You can do this in TensorFlow 2 very easily. And we use also the prefetch command. I have a specific video on this. Now, what I want to show you, what we get back. We get back exactly as I showed you the features. The features, you know, are token IDs and the mask position. So we have here our token IDs. Those are token IDs. And the second part of the feature is the mask position. Here, our mask position. And then, as I told you, we get the labels. Those are our labels. And then, of course, in a tensor form. And then we have here our weights. So again, just to make it absolutely clear, we have two features, our token IDs, where some tokens have been replaced with our mask token, and the mask position that keeps track which token in our sentence, which subword in our sentence we have masked, and the system is challenged to find the corresponding correct token. For the labels, it is simply the IDs that we mask out, so the system knows, hey, there is a mask, and the other one are original tokens. And there's an additional information because not all sequences will have the same number of masks. We also keep a sample weight tensor. Remember, this is our sample weight tensor here, which removes the padded labels from our loss function by giving them the easiest way you can think, 0 weight. Beautiful. So we have our input ready, and now comes the most beautiful part of all. We can build our BERT model, our encoder stack. And we do this, of course, with this high-level API in the toolset called KerasNLP. And they provide all the things that we need to do this easy. So two things I want to point out to you. We have here our token and position embedding layer. This is the very first layer when the original input comes into our BERT model. And then we can build our, if you want, transformer encoder layers here, 4, 6, 12 layers, simply with this command, KerasNLP.layers.transformer encoder. The bread and butter of the transformer model. We have the self-attention mechanism, the feed-forward network. This is beautiful. This is done for us. So we will use this. Just have an idea. Here is the class definition, transformer encoder, all the parameters you can use. Here we have the token and position embedding, so the very first layer, if you want, in our BERT system. Of course, we have some normalization that brings the data to the same scale to reduce some variance in our data with all the parameters you can adjust to. And then, yes, normalization, and then we have a dropout rate, which helps prevent against overfitting of our data. And now we apply all of this now in our model. So here we go. At first, we have here embed our tokens with a positional embedding. So the very first layer, if you want, is here our token and position embedding. Beautiful. So we apply this embedding layer, the very first layer, to our inputs. And what we get is here an output of the very first layer. Unbelievable, huh? Then we do some normalization and we do a dropout. And now comes the beauty. Let's say we want to have here, I don't know, 6 transformer blocks, 6 encoder stacked layers where each layer has a self-attention mechanism and a feed-forward network, as I showed you in my last video. So we say for I in the range of a number of layers is, number of layers, hold on a sec, number of layers is 6 or 8, number of layers. Come on, where's my number of layers? Number of layers is 3. Oh yeah, I told you it's just for demonstration purposes. So you would have here 24 if you're operational. Number of layers, yes, 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 yes. Here, so for I from 0 to 3, we have here now our beautiful transformer encoder layer. We have here all the parameters that we have defined. And we go here. Now our KERAS model is defined by our inputs, defined by our outputs here. And we call it the encoder model because it is not a complete transformer model, but the encoder stack, the BERT model. So, and then we say, okay, let's do this and show me the summary of my model architecture. Model dim is not defined. Okay. Why is model dim not defined? Just hold on. I can't believe that talking I do not execute. We don't need this, we don't need this, we don't need this, and we need this. Yes. So here we go. This is now our model that we built, our encoder model. And you can have here a look at the layer structure and the free trainable parameters. So first we have our input layer, beautiful. And then we have our token and position embedding layer. Then we have normalization, we have defined our dropout. And now come our three transformer blocks, or in our encoder stack, our encoder layers. Here we have them 1, 2, 3, 1, 2, 3. We have defined here the maximum sequence length and the dimension. And this is our model. And now, easy. We have now to pre-train the transformer model. And this is it. We have, as you know, our mask head that we now put on top of our untrained BERT model. And we do the pre-training now with our specific layer for mask language model. This is the head. Yes, it takes about 1 hour and 20 minutes. Because as I showed you last time, the pre-training is really intensive and it takes a lot of time. But the beauty is the fine-tuning is short. So here we go, create the pre-training model by it's just started and then I show you. So we have the input. We have, as I showed you, our token IDs, our features, and our mask position. Great. And then we take here from the input our token IDs. And this is the input to our encoder model that we just built. And then what we receive, you're not going to believe, is the tokens of the model. Remember, this is our encoder model here. This is the model that we just built. And now on this model that we have here, our encoder model, we put now an additional layer, an additional head that we use now for the pre-training. And this is here our command for this mask language model head. Great. And here you have our encoded tokens that we just encoded here with our encoder model and our features that we have here, the input, the mask position. We defined the output. Beautiful. And then we say, here we go. This is our model command, keras.model. We have defined inputs, we have outputs, and now we compile the model. Beautiful. You know, the Adam W optimizer. Git compile is true. If you have seen one of my last videos, you know what it does. Beautiful. And then we have here the pre-training of the model. And of course, we choose the mighty Wikipedia text dataset that we want to do the pre-training on. And here we go, pre-training underscore model.fit. And here we have our pre-training dataset, the validation dataset, and the number of epochs we want to train our model on. And if this is done, we say beautiful, we say save this now for further fine-tuning. And the command, I got a lot of questions from you. How can I save the complete model? Well, it's easy. You say model.save, and then you give here the path to a directory on your disk or here where you want your model to be saved. Yeah, it's still calculating, and it takes about, as I've written here, about 1 hour and 20 minutes. Since I do not have the time, I did already a pre-check, so I just load the result from yesterday. So beautiful, here we go. I've now connected, and now I just say, okay, I know that I have my model on my Google Drive, and it is called the directory encoder model, and now I want to download the encoder model here to our operational directory in this free Colab notebook. It is done. Let's have a look. We should have now an encoder model directory. And if you look now into this directory, you see we have here our saved model, our metadata, assets variable. We have here the whole model now on our disk. So, and then easily you say model, load model, and you give the path to the directory. This is it, and we have it back. Now, as I showed you, we have now finished the pre-training, and now we enter fine-tuning. And now we do, let's do this here. After pre-training, we now fine-tune the model on our SST2 dataset. This is a dataset where we have a qualifier, 0 and 1 for good and bad. We have this dataset, and we want to train now our transformer, our BERT model, on a classification task. We fine-tune it now after the pre-training on a classification task to boost our performance on this downstream task. So what we need, and now this is so beautiful, it is now much simpler because pre-processing for our fine-tuning is now much simpler because we just tokenize our input sentences. So we have here defined a pre-process now in a function. We have just a tokenizer of our sentences, and you know the labels are already available. The labels here you see 0 for negative and 1 for positive. And this is the sentence, and we just tokenize now all sentences from our SST2 dataset. As easy as this is it. Then we use the prefetch command to pre-compute the pre-process batches on the fly on our CPU, like I showed you before. Beautiful. You get the tensor. And now comes the beautiful part. So now, at first we reload our model from disk. Let's say we have done this compilation yesterday, the compiler. So we now say, okay, keras.model.load model, wherever your directory is. And you know, we have our directory here, encoder model. So I load it here now from my directory. Beautiful. Then we take as input, of course, our tokenized input. We have here now, we encode our model, our encoder model with the inputs. And then comes the nice part here. And this is now the pooling layer. In one of my last videos, I showed you the structure of the fine-tuning that's going to happen. We just add an additional keras layer and a layer to the BERT model with a specific pooling layer. And we have here the global average pooling 1D command from keras, where we pool our tokens that we have now at the end of the last layer of our BERT system. And then we have very simple, we predict an output label here with an activation function, whatever you like, ReLU or whatever. Then we have our model, our inputs and outputs from the keras model. And as before, next step is we compile the model and we train the model. Well, you know, to train, we have here the fine-tuned dataset and the fine-tuned validation dataset and the number of epochs for our fine-tuning. And as you can see here, we are now in our last epoch and we have just 8 seconds left. And we are finished in 2, 1, 0 seconds. Done. Yes, beautiful. You see here that our loss went down from 0.4, 0.26, 0.19. Our accuracy increased from 0.80, 0.89, 0.92. Our validation, yes, everything, you know this. And this is beautiful. Now we have a fine-tuned model. And now I want to show you something. When you save this model, you can just save the model in itself. But there is something very special I would like to point out to you, that we have a fine-tuned model and you can now save it with our tokenization layer. And this is really an advantage you have with TensorFlow or with KerasNLP, that all the pre-processing is done in a graph, and so you can make it possible to save and restore the model that can directly run on the inference task on some raw text. So we do not save only the model, but we can save the tokenization. So whenever we do the inference task, we do not have to imply any tokenizer anymore. It is all within our model. This is the beauty and the advantage you have here if you work in TensorFlow against PyTorch. And of course, filming this video in January 2023, TensorFlow is still the most industrial application that is implemented in industry. And you can see there is definitely an advantage here if you integrate this. So let me show you this here. If we now look here in our directory, we have now here an encoder model. And now new is we have the final model. And again, we have the saved final model, the metadata, fingerprint, variable assets, everything. So here you can see now you have here your pre-trained model saved to disk. You have here your final model available. And now let's say we want this has happened yesterday and now it's a new day and we'll do now the model inference task. You remember I showed you we do here 3 tasks. After fine-tuning, we do the inference task. We apply now our pre-trained and fine-tuned model to a particular application. So here we go. So let's say we start new. So the first command you would use is, of course, keras.model, load the model from our path, final model, it's here. Do not compile it because it's already done and we have restored our model. Beautiful. And then, let's do this. And then we start with the inference task. And then we have some input and we have 2 sentences. The first sentence is a negative sentence. Remember, terrible, no go, trash. This is a movie review if you want. And the second sentence is a positive. So we have negative and positive. And you remember that 1 indicates positive and 0 indicates negative. So what we expect now here when we run the inference task, that since the first sentence is negative, we get a 0. And if the second sentence is positive, we get a 1. So let's do this. Let's reload the model here, our final model with all the assets, and then run it on an untokenized input. You have the pure human sentences, the human text, since we already saved here with our tokenizer here in TensorFlow 2. So let's do this. Let's execute this. It reloads the complete model and we run the inference. And here our result, inference of our pre-trained and fine-tuned BERT model is 0 and let's say 1. So 0, as I showed you, is negative. So the first sentence is 0 is negative, and the second sentence, as you can see here, is 0.999. So let's say is 1. 1 indicates a positive sentiment, and indeed the sentence is positive. So system is working. It was, of course, just a demonstration. But if you have now your client dataset or your private dataset, and you build you a transformer model from scratch, just on your dataset, you do not need any political news or any small talk. You are highly focused. You want to have an efficient system on your, explicitly only on your dataset. You can build your own encoder model. You can build your own fine-tuning of the pre-trained model, and you have a model ready to deploy whenever you want. Yes, yes, yes is a modular approach to NLP model building, and really KERAS NLP, if you are familiar with KERAS, which is in itself a high-level API to TensorFlow 2, with this KERAS NLP toolbox, it is really, really easy to build and pre-train your model, to fine-tune your model, and to run inference tasks with your personal optimized model. I hope you enjoyed this a little bit. Here are all the data for you. If you want to run this again, I leave you the link to some other resources on the internet if you want to have a deep dive in certain commands or in certain layer normalization commands. It is easy. I hope you enjoyed it, and I see you in my next video.